Hi everyone. So now that we know how a transistor works, we are going to go through a few circuit example. We're going to start off pretty simple, and then we're going to get to do some amplification, which is very interesting because that's one of the main use of transistors. Um, so let's start with section 4.5 in Steck, which is the transistor switch. It's a very simple circuit, but hopefully it highlight some important current behavior of the transistor. So this circuit has your transistor. Just use the highlighter right here. It's a NPN type because the arrow is pointing away from the transistor. So it has a little resistor there that's going to have a variable value R. We're going to see what that value should be. And we have a resistor that couples to the high voltage, the voltage source, which usually is denoted as VCC up here, but we're going to set that to 5 volt in this case. And then we have a little switch that basically is at VN, and then so the switch will go from 0 to 5 volt up and down, and then hopefully that will turn on a light, which is actually an LED, a light emitting diode. So first of all, let's talk about what a light emitting diode is, because technically that's actually a new component, but by the name, the light emitting diode suggests that it's a diode that emits light. So hopefully that makes sense. This occurs because when the P-type and N-type material, let's just put this right, P, so that's your typical diode, right? You create this little depletion zone between them, okay? What happened is that when current flows through it, right, let's say this direction, okay, the electron current flows in this direction, right? The way this current happened is that these electrons are actually filling up holes here, right? So these electrons are kind of falling into little positive holes here, right? When this happened, the way this energy is conserved is that the electron actually emit a photon. In fact, just the regular diode actually does emit photons. It is actually in the infrared range. This is why we don't see it. But these light emitting diodes are designed so that the energy gap between the electron being in this free state to having it captured by one of these holes happens to be at about 1.8 electron volts, and that actually creates a photon that's visible. In fact, that's going to be a red photon, a red color photon that we can see, and that's why these are light emitting diodes. So for red, orange, yellow type of color LEDs, the diode voltage that's required to turn on one of these light emitting diodes is about 1.8 volts. If you have a green, blue LED, the diode voltage is actually a little higher because there's actually more energy in order to create these green and blue photons, and which is going to be 3.3 volts. So, and the brightness of the LED depends on how much current is passing through it, because the more electrons are falling in these holes, the more photons gets created, right? So the typical current through an LED is going to be about 10 milliamp. It can go up to 200 milliamp, but that's going to be running it pretty hot. So the power dissipated by these LEDs is going to be much less than 1 watt. So if you ever use a LED light bulb, these are actually maybe like a dozen or so LED that are mounted inside the light bulb, and all of them are emitting lights at the same time. Therefore, using maybe 10 watts of energy power, you can off an LED, you get the equivalent luminescence of a 100 watt in the incandescent light bulb, which is the standard we try to compare it to, because that's how we use the light bulb we used to use are something on the order of 100 watts. So you save a lot of energy by using LED light bulbs instead of incandescent, and that's because you're not wasting a lot of the energy heat. Okay? Just like the way we analyze diodes, we're going to analyze a circuit in a transistor on and off state. And therefore, let's see if the switch is off. Let's go circle here, right? The Vin here is at 0 volt. We don't know if there's going to be current across this, but obviously if the transistor is off, what's happening is that no current is flowing from the base to the emitter. So this is the base, this is the emitter, this is the collector. So it's often very useful to label that, especially when you're starting out. Okay. If no current is flowing from the base to the emitter, then no current is flowing through this resistor, right? So if there's no current flowing through a resistor, the voltage does not change, and therefore the voltage at the base is actually 0 volt, which is actually true. Then you don't have this voltage across from the base to the emitter to be bigger than 0.6 volt. Therefore, the transistor is off. So in that case, no current flow through the transistor, and therefore there's no current coming through the collector also, and therefore the LED is actually off. Okay, hopefully that makes sense. But we switch the switch to on, so now we have 5 volts. So I'm going to erase all this, start over, right? I shouldn't have erased the C and the E's. That's okay. Let's say now that Vin is on, we still shouldn't assume that the transistor will turn on automatically, but this turned out to be the case. What happened is that, well, if we have 5 volts here, if we're assuming that the transistor is not on, we actually have 5 volts here, right? Just as before. But the problem is that, well, 5 volt is bigger than ground by 0.6 volts, right? Therefore, that 5 volt is no longer true there, because what's going to happen is that current is going to start flowing from the base to the emitter, right? In fact, the voltage at the base will drop to 0.6 volts, which is the diode drop across this transistor. Okay, so when the voltage across this transistor is bigger than, well, if Vin is at 5 volt, the voltage between the base and the emitter is going to be at 0.6 volt. The transistor actually turns on. Picture S here. Okay, and let's say if we take this R value to be 1 kilo ohm. Okay, 1 k ohm. Okay, let's calculate, see how much current flow through this transistor in this case. Okay, since let's just mark some voltage points here. So here, right, this is at 0.6, so this is at 5, right? That means the voltage drop across this resistor, right, is 0.44 volts, 4.4 volts. Okay, and since the resistor is 1 kilo ohm, we can apply Ohm's law. So the resistor in your transistor circuit still obeys Ohm's law, right? You calculate this, you get 4.4 milliamp, right, from the base current. So what the transistor does when it's on is it amplifies, right, the base current by a factor of beta. In this case, we're just going to take beta to be 100, which is approximately what you'll get with the transistor we're using in the lab. So when you amplify this by a factor of 100, you get 440 milliamps. Okay. So what happened is that this is actually not true, because the collector actually cannot supply this much current. Okay. And in this case, the transistor is actually functioning in this place called the saturation mode, where we're maxing out how much current it can output, and therefore we actually get the saturation current, not this, beta times IB current. Okay, so what is this saturation current? What is the real current that we're going to get? Okay, so we can do a little analysis here. Okay, let's go up, back up that picture. So you have a resistor here. We're going to use to call this RC. And we also know that the voltage drop across this diode, since it's a red one, is going to be 1.8 volt. Okay. So we do a little analysis here with some Kirchhoff's loop law, Kirchhoff's voltage law. Okay. So I'm actually going to redraw that because it's a little bit confusing the way it is. So we have voltage VCC. We're going through a resistor. We call that RC. And then we're going through a diode. It emits light, but it doesn't matter. But the voltage drop across that is going to be 1.8 volt. And then this goes into a, oops, this goes into, I'm going to give myself a little bit more space. It's the keyboard. I have enough space, it's fine. Okay, it's going to go through here, and it's going to go to ground. So ground is here. Okay, there's going to be one more thing we're going to note, is that the voltage between the collector and the emitter has to be bigger than 0.2 volts. And this is just so that you're driving current from the collector to the emitter, otherwise no current flows through. So if we apply Kirchhoff voltage law, right, we start at VCC, we're going to call this the collector current, which is actually what we're trying to calculate. It's going to be equal to, so VCC, if you go across the resistor, you drop in current, it's drop in voltage, it's IC RC. The diode drop is 1.8 volt. And we're going to have another drop across this transistor. It's going to call that VCE for collector emitter. And then at that point, we get to ground. Okay, solving this equation for IC, flip this over. So it's actually VCC minus VD minus VCE, second right. Okay, all divided by RC. So this is 5 minus 1.8 minus 0.2 divided by, well, RC in this case is actually 330 ohm. So it's actually, what is that? That's 3 volts divided by 330 ohm. Okay. Trying the calculator. So it's about 9 milliamp or something. 3 divided by 330. Yeah, well, 9.1 milliamp. Off a little bit. Okay. So this is actually the current that comes from the collector that goes through the LED that's actually lighting it up. Okay. So in this case, right, even though, right, the beta is 100, we're actually not amplifying the current by a factor of 100. In fact, what was the base current? 4.4 milliamp. We're actually amplifying it by just a factor of 2, which is fine. So the beta does not have to get used up, right? That's the maximum application that the transistor can do. But, right, in this mode, right, the transistor is basically considered fully open. That means, you know, it's not limiting the amount of current. It's actually the resistor at the collector that's limiting current. And it's actually working in this mode called saturation mode. Okay. In this mode, right, let's say, you know, my little switch doesn't give me 5 volts. It's actually giving me 4 volts, right? We made a DC power supply that, you know, that has too much of a ripple voltage, for example. So in that case, right, even though you reduce the base voltage to 4 volts, the LED still turns on and has the same brightness, because, right, in that case, you just kind of reduce, you know, the base current a little bit, but the beta will actually increase. Well, the effective beta that's actually applied will increase, so that you're still getting about 9 milliamp through the LED. So the LED brightness doesn't change, even though your input voltage is changing slightly lower. Just, you know, what you want is a switch, right? So we could make this switch to be a dimmer instead, where depending on the input voltage, it actually changes how bright your LED is. In other words, we can control how much current flows through the LED by changing exactly how much how close we get to 5 volts on this input switch. Okay, so in that case, all you have to do is swap R in to be a much bigger resistor. Okay, so in this case, right, let's see. So let's say we have 5 volts. Let's start off with 5 volts again, right? Instead of, right, the base current being 4.4 volt divided by 1 kilo ohm, the base current, right, is now 4.4 volt divided by 100 kilo ohm. Okay, so 100 kilo ohm, so reduce that by a factor of 100, so that's actually 44 microamp, right? Okay, 44 microamp, right? If your amp gets amplified by beta, and we're assuming beta is about 100, let's go clear, right? 100, right? That's actually times 44 microamp, right? This is get us back to 4.4 milliamp. Okay, so in this case, right, the collector current here, right, is not maxed out by the it's not maxed out because you're not close to, where is it? You're not close to this 9.1 milliamp current, right? So basically, the max IC you can have, right, is actually 9.1 milliamp. So you're not close to that. So in this case, the LED is gonna turn on, but it's gonna be, well, if the power is this IV, power is about half as much. I think the brightness of it actually goes down by 1 over square root of 2, so it's about 70% as bright. Okay, so in this case, this is known as a forward active mode, meaning the current is running forward through the transistor, okay, but changing the input voltage just slightly. Let's say if we drop the input voltage down to 4, I'll let you do that calculation. You actually reduce the base current, which then in turn reduces the collector current. Then actually the amount of power that comes out of LED changes, so you can actually dim the LED by reducing the voltage input. Okay, one thing to note, right, this is capped at 5 volt. The VCC is at 5 volts. So you do not want to go to 6 volts, because remember what happens that when you go above 6 volt, you can actually reverse this. In this case, it actually doesn't bother it. The thing just doesn't work because you're going to start reverse biasing this LED actually. Okay, so now we have a switch that's actually a dimmer instead, which is pretty neat. Okay, right, so I'm going to go through the next circuit because a lot of the analysis technique that's used is going to be very useful. So we're not going to add any components to it, and this is going to be the emitter follower circuit, which is a very simple circuit. Typically you actually have an input resistor that blocks the any DC bias from running a current backward, but that's just a protection thing, so it's not essential to the physics of it. It's just more of an engineering thing where you want to protect your voltage source from your power supply, and vice versa. Okay, so this type of circuit, right, only cares about the AC signal. It doesn't care about the DC. Okay, because the DC is just going to give you a flat line. It's actually the AC signal on top of it that gives you some information or some power transfer that you care about. So for, let's just draw this as an example, right? Let's say you have a signal like this, right? Where you have voltage as a function of time. Right? This is time, right? And I'm going to draw a dotted line here. Okay, let's say the signal starts like this, goes up and down, right? Okay, this is actually known as the DC offset, which is denoted as V0. okay? And the voltage as a function of time is actually V0 plus the time varying part, okay? Plus, and the time varying part is going to be a little bit hard to see if you're writing it because it's denoted with just a lowercase v, okay? So I'm going to try to put the parentheses t, that way we denote that it's a function of time, and in fact I'll put little caps on top of the capital T, which represents the total voltage, which is the DC part plus the AC part, okay? Similarly, you can define current this way, where you have a constant current and then a time varying current on top of it, and that's actually your total AC and DC components of a current. So analyzing this, right, we want to figure out what V out is. Well, V out is going to be whatever the emitter voltage is. Once again, I'm going to mark these. This is the base, this is the collector, right? Okay, VE stands for what the voltage is at the emitter, okay? Because V out is taken at the emitter, that's why this is equivalent. And we know that, right, whatever the base voltage is, right, if you drop it by 0.6 volt, that will turn into the emitter voltage, which is just one diode drop, okay? But, right, this negative 0.6 volt is just a DC offset. It's actually a constant, right? So let's write that out and see how that looks like, right? V as a function of t. Let's do that. And right, VE as a function of t, right, equal to some V naught E, that's constant, right, plus some time varying component, right? And this negative 6 volt DC offset, right, is just in that constant. So if we only care about the AC part, right, V out is actually going to be whatever V in is plus VB, okay? So this DC off, this diode drop of 0.6 volt just disappear when you're dealing with just the AC part, okay? Right. So this is kind of useful because now you can calculate what V out over V in is. It's actually pretty boring because if you just solve this, right, because this is actually, VB is actually the base, the input voltage, right? The ratio between them is actually just 1. All right. Okay. This seems like a useless circuit, right? Why would you do this? Okay. But the thing that's kind of cool about this is that the voltage stays the same, but the current gets amplified. Okay. Whatever current is going through the base, it gets amplified at the output by a factor of beta plus 1. The reason it's plus 1, let's go back up here, right? So you have current that's from the base, right? But you also have current that's from the collector, right? The emitter gets both, right? So it's beta, so IC, right? And then IC, right? This gets amplified by the transistor, okay? I beta plus IB. So therefore, it's actually 1 plus beta times B, right? That's where that 1 plus beta comes from. Okay, so the current gets amplified, but the voltage does not. Okay, and this is going to have an effect on your input and output impedance, the stuff we talk about in the first module where we're dealing with DC circuit. The same thing applies to AC circuits, of course, and maybe even more because a lot of times you actually want to do impedance matching, and a transistor will allow you to do that. So let's say we have, just review what happens in DC, right? Let's say we have some device that has some low input impedance, that meaning, well, I'm going to connect this to some R load, right? And let's say R load is small, right? Maybe like 10 ohm, 50 ohm, whatever it is. Okay. In that case, right, the voltage divider, right? Let's say, you know, these are the same, like 1K, 1K, right? And you had a 10 volt supply, right? You expect that V out to be 5 volt, right? But if you have R load, let's say that's 100 ohm, right? You can calculate this. It turns out that VL is going to be substantially lower than 5 volts. Okay, in fact, this will be pretty low actually. It just drops down to like less than 1 volt. Okay, so you know that like when you're connecting a device to something, you want the input impedance to be fairly high. Okay, so how does this connect to this emitter follower? Okay, so let's say we have some device, I don't know what it is, it doesn't actually matter, right? It has some input impedance, and input impedance is basically telling you if you have whatever the voltage input is divided by the amount of current that goes through this device, right? That's the input impedance. Okay. If we put a common emitter follower in front of it, right? Make sure I put the resistor in the right place. Oops, a little bit too hot, too low. Okay. Let's just draw this line so it's going to the right place. Okay. Right, VE. This is the emitter. This is RE. Right, and this is some VCC that we connect to. Up here, yeah. Okay. In that case, okay, what happened is that, right, since the input impedance, right, instead of this spot, as I'm highlighting green being the input, now we move the input to the front of the transistor. Okay, right. And once again, we're just going to keep using the same definition where the input impedance, instead of being here, right, now we have to calculate it being here, right, is the voltage, the base, divided by the current that drives through the base. But we know that the current that drives through the base gets amplifies it to the output side of your amplifier of your transistor by a factor of beta plus 1. So therefore, right, the current through your base is actually reduced by a factor of beta plus 1. In fact, right, the load, if you convert this current to VE over the load current, I guess they call this load instead of ZN. That's fine. The load of your device, okay? What happened is that you basically increase your device's input impedance by a factor of beta plus 1. So typically this will be about 100. Okay, and this is very useful because, right, you want your device to have high input impedance so that you're not drawing too much current on your voltage divider or whatever you're connecting to. Therefore, you're not affecting the other device you're connecting to. So it's the output, right, that you're connecting to input, so you're not affecting the output side on the other device. Okay. For future reference, just to make sure everyone have this definition, hopefully it's not too abstract from this point. You can think about a device having a input impedance, right, like this, but it can also have an output impedance. I think I already used this, right, where the output impedance is basically the output voltage divided by the current that comes out of that device. Okay. Right, so how much time did we do? Okay, so I'm going to do one more circuit, right? So this will go a little bit over 30 minutes. Okay, so because we're going to get to see our first amplifier. So this is the common emitter amplifier. So this will be kind of your first time you're going to see V out being bigger than V in. Okay, so it's basically the same circuit as above, but we're going to put in a collector resistor here, and we're actually taking the input at the collector instead. In fact, this is going to be an inverting amplifier. Okay. So once again, we're going to separate the AC and the DC part of signal into the constant DC, and all we care about is the the AC part. Okay, so if we analyze this, right, we care about, let's see, we care about how much current is going through this collector resistor, because that current is going to give us a voltage drop that will determine what Vout is, right? If whatever VCC is minus this current voltage drop across the resistor is going to be your Vout, right? So it's actually, let's say your VCC is 10 volt, you actually cannot go above 10 volt. Okay, we're going to see some limitation and how we can mitigate this with some pretty cool circuits that that will allow us to deal with a DC offset. Okay, so I'm going to define also the current through the emitter. Right, this is the base, this is the collector, this is the emitter, and we also have a base current here. Okay, so at this point is the voltage at the emitter, right? When the current travels through this emitter resistance, it goes to ground. So this makes the analysis, this is a good starting point because it's very simple, because the voltage at the emitter, right, is going to equal to I, the current through the emitter, times the resistor at the emitter, right? Because you're dropping the voltage to 0, so it's technically be a -0 there, but we're going to write it. Okay, but the voltage at the emitter, right, is also equal to the voltage at the base minus this 0.6 volts. Okay. The other thing we're going to do is we're going to say that, well, since the collector current is approximately beta, the base current times 1 plus beta, right? Oops, not that, sorry. It's just beta times the base current. So the beta times the base current gives you the collector current, right? And then the emitter current is basically whatever the collector current is plus the base current, right? Right, and that's actually going to be, since the base current is going to be smaller by the collector current by a factor of beta, right? Well, in this case, about 100. This is the emitter current is approximately what the collector current is going to be. So we're going to do that substitution also. Okay. So, so if we divide, so we do the substitution in here, right? We replace this with IC. Let's just do it. Do more algebra steps. So it's a little bit easier to understand. E, right, equal to goes, right, base voltage minus 0.6 volt. Okay, I'm going to divide both sides by RE. So the collector current, right, which changes with time, so that's the total, right, it's going to be, right, some constant current plus some time varying current through that collector. Okay, and that's going to be some constant voltage at the base minus 0.6 volts plus some time varying at the AC part divided by RE. So this constant current corresponds to this constant voltage, right? So if we only care about the time varying part, well, we find that, well, the time varying part here is going to be equal to the voltage, and that's the voltage across the base. Forgot about that. Pen, keep working. RE. Okay. All right, and now we get to this point in the book, right? Equation 4.24, where the collector current is going to be equal to the base voltage divided by RE. Okay, all right. So that's our first equation. And similarly, we can do the similar analysis with from VCC, oops, up here, and how it crosses this resistor, and that's how we can get to V out. Okay, okay. In fact, this is V out. Okay, why the book doesn't write that. Okay, so the voltage, is that it? No, so sorry. V out is actually VC, right? Sure that's correct. Okay. So with a similar analysis where you're separating the DC term and the AC term, you're going to see that while the voltage at the collector, okay, is going to be minus the current, the AC current through the collector times the resistor at the collector with a negative sign, of course, because you're doing a voltage drop. Okay. So now, okay, if we want to compare, we substitute in IC from here, we're going to find that, well, the collector voltage is going to be proportional to the base voltage on the AC portion times RC over RE with a negative sign in front of it. Okay. And going back to the circuit, right? This is VC, this is VB, right? This is VE, right? This is actually your VN, right? So VN is your VB, okay? So we put that replacement here. V out is your VC, so we'll do that replacement there, okay? And when we're calculating amplifier, the thing we care about is the ratio between V out and VN, and therefore that's actually known as the gain with a big letter G. If we do this division, we find that the gain is actually going to be negative RC over RE, okay? And that's the gain of our common emitter circuit with a negative sign. So whatever signal you drive in there is going to get flipped upside down because of this negative sign. Okay, so I'm not going to go through 4.9. I'll do that next lecture because I'm already over time.